Hello everyone, my name is Emmanuel Olakwede, and today I'll be talking about the synthesis and applications of aspirin. The history of aspirin extends back to the time of the ancient Egyptians and Sumerians, in which they used the bark of the willow tree to relieve joint pain and inflammatory pain due to injury. Indigenous people in South Africa and Native America also used the willow bark to treat headaches and fevers. The compound that was actually responsible for this pain-relieving effect was salicin, which is a compound that's found in the willow bark and one that is also metabolized in the intestine of humans into salicylic acid, a precursor of aspirin. Beginning in the 16th century, salicylic acid and many of its derivatives were passed through many reactions to look for a stable form that could be offered as a drug to the public, which eventually led to this discovery of acetyl salicylic acid, or as we commonly know it, aspirin. The picture on the right shows the timeline of many of how salicylic acid and many of its derivatives were found before they were eventually turned and procured into aspirin. Aspirin was discovered in the late 19th century by Felix Hoffmann, a German chemist. He did it under the supervision of other scientists, and what he did was he focused on the phenol group and was able to successfully, the phenol group right here, and he was able to successfully acetylate it into this acetyl group. Many of the scientists at the time actually only focused on the carboxylic acid, and in doing so they weren't able to find a stable form, but by Hoffmann being able to focus on the phenol group, he was able to acetylate it into this acetyl salicylic acid that we commonly know today as aspirin. Now, aspirin can actually be synthesized in one of two ways. The first way is mixing salicylic acid with an acid anhydride in the presence of concentrated acid or concentrated sulfuric acid, or better still, we react the same salicylic acid with acetic acid in the presence of an acid catalyst. However, this way is quite slow and it has a relatively low yield. As a result, we prefer the first way, in which we react salicylic acid with an acetic anhydride to form aspirin and acetic acid. This is the mechanism for the synthesis of aspirin. The first thing is that the acid anhydride or acetic acid in this case is protonated to form this intermediary. This intermediary then reacts with the salicylic acid, in which this oxygen on the salicylic acid kind of acts like a nucleophile to form this protonated product. And then we transfer the proton, so the proton is transferred to an adjacent oxygen by the presence of this conjugate base, in which we remove the hydrogen from here, we deprotonate it here and protonate it here. By doing so, we create a good leaving group, as one can see here, which is, when it leaves, forms acetic acid. When it leaves behind this also positively charged product, which we can also deprotonate to form acetyl salicylic acid. Why acetyl salicylic acid? We can see here that acetyl salicylic acid has this acetyl group and this carboxyl group along with this ring, and the salicylic acid only has the ring, the carboxyl group, and a phenol group, all of which can stabilize salicylic acid for resonance and induction, but the presence of this acetyl group on aspirin actually further stabilizes it. And I believe that through this further stabilizing in resonance, that it is a more stable drug, and then it has a less potential of being harmful when consumed as a drug or a pill. Here is the metabolism of aspirin. So we all know that aspirin is used as a drug in our body. What makes it a particularly good drug is that aspirin inhibits enzymes which make some chemicals that could have inflammatory effects on the cells in our body. For one of those chemicals, for example, is thromboxane. Thromboxane is a chemical that induces the aggregation of platelets in the blood. In other words, platelets will literally gather in the blood of the veins, and they will block the veins and the arteries. They could lead to cardiovascular problems, which could be potentially damaging to our human health. So here we can see that the protein which synthesizes thromboxane, without, in the absence of aspirin, everything synthesizes directly. The thromboxane is synthesized and the platelets production is activated. However, when aspirin is present, the aspirin actually acts as an inhibitor by binding to the active site. As we can see, the acetyl group actually binds to the active site and renders it functionless. In other words, it can perform its function of producing thromboxane, thereby inhibiting it, and as a result, we alleviate the risk of cardiovascular problems. The fact that aspirin can perform such a metabolism and other similar metabolisms is what makes it a very potent drug in combating diseases. Now we have our references, and I would like to thank you for giving me your time to learn more about aspirin and the synthesis of aspirin today. I really hope you did learn something from this short video, and I hope you have a nice day. Thank you.